Today we're going to look at 2-1 and 2-2. So starting in 2-1, we're going to look at represent relations and functions. Okay, so we have represent relations and functions. And we're going to look at basically 4 different ways that we can represent functions. So one way that you can represent functions is by using ordered pairs. So ordered pairs are like points on a coordinate plane. And this would be the x value first, and the second is the y value. Otherwise known as, the x value is also called the input, and the y value is also called the output. And then the other way to call this is domain. The x value is also called the domain, and the y value is called the range. So ordered pairs show us x and y. They show us input, output, and they show us the domain and the range. Alright, and then next we can also represent these using a table. So in a table, basically it's like a T-chart is what I always call these. So we have the same thing, like, oops, I'm going to make that a 1. So we'd have like 1, -2, and then 2, -3. Very similar to what the ordered pair looks like, except for it's in table form. And again, these 1s and 2s are the x's, the -2 and -3 are the y's. These guys are the inputs, these guys are the outputs. The x's represent the domain, the y's represent the range. Another way that we can do this is also on a graph. So basically we would just plot the ordered pairs or plot the numbers in the table. So 1, -2 is here, and then 2, -3 is here. And so again, we have the x's and the y's, right? And that's how we got the ordered pair. We went over 1, down 2. We went right 2, down 3. And again, we have the input, the output, the domain, and the range. So the last way to do this is called a mapping diagram, which is kind of like the table with a little extra arrows. So we have the input and the output. Again, remember, input is just a fancy name for x's, and output is just a fancy name for y's. And they kind of got like these little bubble looking things, like ovals. Right? And I'm going to put the 1 and the 2 in here because those are our input numbers, and the -2 and the -3 in the output bubbles. So what you do is you map what 1 goes to -2, just like up here. You have 1, -2. So I just draw an arrow that represents that mapping. And then 2 maps to -3. So these are all the 4 the exact same thing. It's just a different way to write them. Alright, so let's look at how a relation can be a function. Right? So not every relation can be called a function. A function has to have where an input has exactly one output. So let's look at an example here using a mapping diagram. So if we have the following inputs, -3, -1, 2 and 4, and then we have the following outputs, 2, 3, or 3, 2, and then -4. Right? And the mapping looks like this. So if -3 maps to 2, and that's given, so I'm just telling you what the problem is, and then -1 maps to 3, 2 maps to -4, and 4 maps to -4. So we want to know, is this a function? So the answer is yes, because one reason is that there's no inputs that repeat. So each input is its own number, right? We have a -3, a -1, a 2, and a 4. And so that means that this 2 only maps to this -4. It doesn't go anywhere else. Every time we input a 2, we will always output a -4. It does not matter that this 4 has the same output, because as long as every time we input a 4, we always get a -4 out, then it has its unique output. In order to make this not a function, let's say that we have another 2 in the input section, and I want to make it now map to a -3. This is now no longer a function because 2 is only supposed to map to -4. If we have this additional 2 that now maps to a -3, that breaks this relation. It can no longer be a function because every single time in this problem we have a 2, we must have an output of -4. Okay, hopefully that makes a little bit of sense. If we look at domain and range, the domain in this problem would be the -3, the -1, the 2, and the 4. And they go in these little squiggles. That's set notation. So we'll pretend like this 2's not here anymore since I broke it earlier. The range is all of the outputs, or all of the y's. And this would be, usually write them in numerical order from least to greatest. So this would be -4, 2, and 3. Right? And again, with the set notation, they're just little squiggles. And so that's what, this is what a function is here, where each x has its own y. And then the domain is all of the x values, or the input values, and the range is all of the y values, or the output values. Alright, so now let's look at the vertical line test. A vertical line test is a way to look at a function graphically and determine whether or not it's a function. So, for example, let's go ahead and draw this graph. We have a coordinate plane x, y, and then we're going to have this function, basically this is y equals x squared, right? And so we want to determine if this is a function. So what you do, you basically draw a vertical line at every single point on this graph. So really you're kind of doing this with your eyeballs instead of having to draw an infinite number of vertical lines. But if at any point the vertical line touches the graph in more than one place, it's not a function. So if we look at this, every single vertical line we drew only touches the function in one place. So therefore this is a function because it passes the vertical line test. So here's an example of one that does not pass. So we have this graph here, and if I drew vertical lines, we can see the first one already fails because it touches the graph in 2 places. So this is not a function. So if we go back and look at the definition of a function, the reason it's not a function is because at this x value, it has 2 different y's. And remember, x can only map to one y. It can't go to the top y and then go to the bottom y. It can only go to 1, so this is not a function. The second lesson for today is about slope. So remember that the variable for slope is m, and then the equation for slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? So if I want to find the slope of the line that passes through the points 2, -4 and 4, -1, the first point's x sub 1, y sub 1. The second point is x sub 2, y sub 2. Remember, x's go first, y's go second. Because this one's the first point, he gets the 1s, and the second point gets the 2s. So we just plug it into our equation. So y sub 2 would be -1 minus, so this is the minus from the equation, and then y sub 1 is -4. Over x sub 2, 4, minus x sub 1, 2. And then because we have minus and negative, we always change that to plus or positive. And we get 3 over 2. And then it's going to ask us to tell whether the line rises, falls, is horizontal, or is vertical. So because this is positive, it rises. If this was negative, it would fall. And if it was 0, it would be horizontal, and no slope is vertical. So positive, whenever the slope is positive, we're going to write rises. Whenever the slope is negative, we're going to write falls. Whenever the slope is 0, 0 on top, so 0 over anything on the bottom, so I'm going to put K for anything, then that's horizontal. And then whenever it's no slope or undetermined, then it's a number over 0. So I'm going to write NO to kind of remind us for a number over 0, like no, and then that's vertical. Okay, so if you know how to find the slope, and then you need to know how to determine if it rises, falls, horizontal, or vertical. The next section says to tell whether the lines are parallel, perpendicular, or neither. So remember that parallel lines have the same slope. We studied that in geometry, so that should be pretty familiar. Have the same slope. And perpendicular lines, my pen is not liking me today. Perpendicular lines have opposite reciprocal slopes. And again, we remember that from geometry as well, I hope. So parallel lines, remember, look like this. Lines that do not intersect. And then perpendicular lines are two lines that intersect at a 90-degree angle. So these two slopes would be the same. M would equal M. And on the perpendicular lines, a slope would equal a slope with the opposite sign, and then the reciprocal, which would be 1 over whatever the slope was. Okay? So hopefully you have that written down in your notes. If you need more time, just stop the video, write it down, and then continue. Alright, so let's look at an example. Let's look at line 1. It passes through the points -2, 8, and 2, -4. And then line 2, we'll write in black, passes through the points -5, 1, and -2, 2. Right? So we want to determine if these lines are parallel, perpendicular, or neither. So remember that the equation for slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. The first number in the ordered pairs, we have x sub 1, y sub 1, x sub 2, y sub 2. Same thing down here, x sub 1, y sub 1, x sub 2, y sub 2. Alright, so let's look at the first equation in green, or the first line in green. So we'll plug in the numbers into the formula. So -4 minus 8 over 2 minus a -2. So plus a positive. So this is -2 over 4, which reduces to -3. Now let's look at the line that's in black. So plug them into the equation. Y sub 2 is 2 minus 1 over -2 minus a -5. So plus a positive. So we're going to have 1/3. So if they're parallel, these would be exactly the same. They're not exactly the same, therefore they're not parallel. If they were perpendicular, they'd have opposite signs. So this one's a negative, this guy's a positive, and then also if they're perpendicular, they would be opposite. They'd be opposite signs and reciprocals. So the reciprocal of 3 is 1/3. So therefore these are perpendicular because they have opposite signs and they are reciprocals. If they were not the same and they were not opposite and reciprocals, then it would be neither. Right, hopefully that makes sense. You've done this before in both Algebra 1 and Geometry, but please ask questions tomorrow if you need a little refresher.